Welcome, everybody, to the most interesting lecture of the semester. So we are going to start today right away with a question that I have for you, and it is right there. What is the most accurate definition of a normalized type? I will start the quiz. Is it an equivalence class of postings? If two postings have the same document ID, then they appear jointly on the index. Or is it the resulting set of a query expansion used to query the index? Or is it an equivalence class of documents or an equivalence class of tokens? We have 16 answers so far, 19. See the live results. Wow. You are correct, indeed. This is an equivalence class of tokens. It's this idea that whenever we have the same verb conjugating differently, or a computer computing, computed, you want to group these things together and consider them the same. And this is what we call a normalized type, right? Or many people just say type, right? Normalized type. The others are just made up. Equivalence class of postings, that's not meant to make any sense. The query expansion, remember that it is asymmetric. These are not equivalence classes at all. So we cannot even talk about any normalized type or anything, because normalized type basically supposes there is an equivalence class and you have a normalized representation of that class. And it is also not an equivalence class of documents. Okay, thank you very much. So we are now ready to continue. And I'm going to recap on very quickly on what we've seen so far just already, and then we'll move on to the rest. So remember that at that point, we have the standard inverted index. We made a few modifications to it. We have the byword index. We have the positional extension of the index. Then we looked into a tolerant retrieval. We looked into how to implement wildcard queries, right? When you have an asterisk that is a joker for some letters that you don't know what they stand for. We saw that it's quite straightforward to solve a wildcard query if the asterisk is at the end. If it's at the beginning, you can build another index that mirrors all of the terms, and then it does the trick. If you have a wildcard in the middle, then you can combine the two, but remember that we had false positives. So we needed to do some additional filtering. And then we had another way, which is the permuterm index, where you remember that we rotate all of the terms, putting a dollar in the middle, and then we just rotate it and create yet another index structure that allows us to recover terms given the letters at the beginning and at the end, right? So this is for when the wildcard is in the middle, but then without the false positive problem. And I think this is where we stopped, right? So the next thing I'm going to show you is k-grams. In fact, we've kind of already seen them with k-words. Remember the byword indices, k-word indices, where we have this sliding window over the documents that eats 2 words or 3 words at a time, and then we look at all of the sequences of words that follow each other. Well, we are going to do exactly the same thing, except that instead of doing it on documents with the words, we are going to do it on the words with the letters. So this is what k-grams is. what k-grams are. And that allows us to answer this kind of queries where we might have a wildcard at the beginning and at the end, which is yet another kind of query. So let's take an example. That is the word computer. And I'm going to show you the 1 grams. That one is easy. It's just one letter at a time, right? We have COMPUTER, but also the dollar, because we are going to add a dollar at the beginning and at the end. That shouldn't surprise you, because we've already been doing that for the per new term index, right? Where we use the dollar as a special sign that signals the beginning of the or the end. But here we need it both at the beginning and at the end, because we don't have a ring like for the per new term index. So we don't rotate or anything. We just have the dollar at the beginning and at the end. Okay, can anybody guess what the 2 grams or the bigrams would be for computer, giving these dollar signs? Anybody can guess? The bigrams, 2 grams. Or you can write it on Zoom if you want. Any bigrams? Who wants me to show them? Okay, I'll show them. Here they are. $C, COOMMPPUUTTER, $. Sliding window. We just slide a window, 2 letters at a time, over the words from the left to the right. Okay, maybe you can try the trigrams, 3 grams. What are these? Who would be able to do it, but just doesn't dare to raise their hand? I promise I will not ask you. Very good, very good. So did you have this in mind? Yeah, okay. So $CO, COM, and so on. And then you guessed it, so this is how it works, right? The sliding window of size K, and we just slide it over. Exactly the same thing as for the words, what we did with the byword index, but now we do it on letters, okay? So these are called k-grams. Now, as you might have guessed, 1 grams are not very useful. If you have very long k-grams, like a high value of k, it's not very space efficient. You remember for the k-word indices, the problem that we had when we had k too high, because then the number of entries in the index just explodes. And so we kind of like this area here, right? 2 grams, 3 grams, 4 grams. By the way, 2 grams, bigram, it's the same thing. Trigrams, 3 grams, it's the same thing. It's just a different wording based on a preference, right? I don't know if anybody says quadrigrams or 4 grams, but anyway. So these are the k-grams. What are they useful for? Well, they are going to be useful for comparing words and to understand how similar words are going to be, and or to spell check the words when there is a spelling mistake. So what we're going to do is take several words. For the example of this lecture, I took 2 of them, but of course you would do it for every single word that you see in your collection. So these are the 3 grams for Terran, $TE, TER, ERR, RA, RAN, and so on. Who agrees with this? Okay. So then what we do is we build an index. We love being indices, right? So we just love building indices. And here's yet another index. We are just taking all of these 3 grams. And we are going to build, as always, some sort of B plus tree or something like this, or maybe we don't even need a B plus tree that is as large as usual. Maybe a simpler version of a tree is enough. But anyway, we have a tree like this, and that allows us to efficiently look up the k-grams, in that case, the 3 grams that we have. And every one of the leaves of our k-gram index, that's what it's called, points to the words that contain these k-grams. For example, COM is contained in computer. Sometimes it's several words, right? TER is contained in computer and in Terran, right? So we have this index of all the k-grams, and every k-gram points to some list of all the words that contain it. So far, so good? Okay. So now, imagine that we have this query right here that the user just typed, asterisk, asterisk. How do we find the words that contain, that basically fits this query? What do we do with the index? Who knows the answer to this question but doesn't dare to raise their hands? I also promise I won't ask. Who knows what we do with the index? Nobody? So we can just take this COM and look for it, right? So what is the algorithmic complexity of this? Logarithmic, I'm slightly hearing, right? So indeed, in logarithmic time, we can look that up. Then we find the k-gram and the words. What about this one? What could we look up here? It's difficult to break the ice today. We are not yet on summertime. It's going to be harder next week when we are on summertime, or the week after that. Yes, I see a raise hand. Yes? Mm-hmm. Mm-hmm. Yes, so that would be a possibility. I'm repeating on the microphone for the people on Zoom. You suggest that we look for TER and then CO anything, right? The range exactly like we did last week with the wildcard indices. What if I tell you to remember the dollar at the beginning and at the end of our words? Would you have any other ideas that wouldn't involve a range? Because it would start with CO, right? So what k-gram do you think we could have? Anybody? Mm-hmm.
It says ER $sign.
Yes, ER $sign, and another one. This is absolutely correct. And another k-gram we could look. $CO, exactly. Yeah, that's exactly it. So $CO, TER. I could also have put the ER dollar. I just didn't do it, but we could have as well. We basically want to narrow down, right? And when we narrow down, we can post filters. So even if we didn't use them all, we can still narrow down. So that's it. And now we see what is the word that has them in common. It is computer, right? As a human being, you probably already saw it from the query, right? But we need to tell the computer how to do it. All right, so with this index, we can answer this query because we can locate the word or the words that fit this wildcard query, okay? So now, this is going to be very useful, not just for answering these kind of queries, but also for the spelling correction. Because we might make mistakes when we type a word in a query engine. Who has ever made a mistake and gotten the Google message, did you mean that? Okay. Who has already been even corrected that Google directly went ahead and corrected your query without even asking you? Yeah, it happened, right? And in it, there's all these approaches. You can always query for the corrected terms. Maybe you give an option to not do it. Or you can only do that if they are not in the dictionary, meaning you look them up in the dictionary. You remember that the vocabulary is the set of words, and the dictionary is the data structure that indexes the vocabulary. So you can look them up in the dictionary, and if the corrected terms are not in there, then you can correct it. Or you can correct if they are not in the dictionary and they are not enough results, because it might be that you have that the word is out there on the internet, even though it's not in the dictionary. Maybe because you didn't index all words, or those that are very rare, you didn't bother, I don't know. So you do it if there's not enough results. Or you are super conservative. You don't even want to just correct anything. You just make a "did you mean" kind of message to the user, and the user can choose if they want to take the spelling correction. But the question is, how does that even work? How is Google able to tell you so fast that you might have meant something else? Well, there are ways to do that. One common way to do that is called the edit distance or Levenstein distance. Who has ever heard of this? Wow, I'm super glad. So this is going to be a refresh, basically. Who never heard of this? Okay, you know it. So I'm going to give you a perspective. Who knows that this is also used for the diff algorithms on Git and so on? Who didn't know that? right? It's the same algorithm, the edit distance, that is also used to compute the diffs when you commit code to a repository. Just again, with this idea that instead of doing it with the letters, you do it with the lines. Always a matter of granularity. Okay, so here's my perspective on the Levenstein distance, which you already know. We want to figure out how far away these two words are. So for example, we could think we can go from or to 2 by removing r and then adding t. That's a distance of 2. Or we could change the o to a t and the r to an o. That would be replace. That's also a distance of 2. And basically, we want, as you remember, to minimize the number of such changes that we make. And so the way to approach this could be brute force. What if it's brute force? We search for absolutely all ways of doing that. So we start with, let's say we want to change or to 2. Then we could subdivide it into different ways. Either we arrive from or to 2 by first converting or to t and then adding the o, or we went from or to 2 by first removing the r and then using the edit from o to 2 recursively, or we know how to do it from o to t, and we do that, and then we replace the r with an o, right? It's a recursion, right? We just try to do it with an induction that we do one operation and then the rest is recursive again and again and again, right? You can recursively find out all the ways to solve the problem. So every one of these squares is basically a known problem. Like for example, if you are here, this is the known problem of converting O to T, and based on that known problem, then you can solve that one. And this is the one we ultimately want to solve. Who sees that this is just exploding the space, and that is absolutely not going to work in this way, in a computationally tractable way, right? That was just 2 letters here, and look at already the size that it has. So this is not tractable. However, the insight here is, if you look further, if you look closer, you realize some of these boxes are the same. You see, O to T, nothing to 2, O to nothing, O to nothing, O to nothing. You see, it repeats. And when we see things repeating, our mathematicians' brains tell us, let's build equivalence classes and group them. That's exactly what we are going to do, right? So that's just a resolution path for one word. So depth first search would be completely intractable computationally. So would be breadth first search. These are the 2 ways of doing that. We basically want to find the shortest, the shortest path. So equivalence classes are nicely painted in green and in yellow and in red and in orange and in blue, all of those that are basically the same. And now we are going to use our mathematical cooking recipes to merge all of these in equivalence classes like this. And now, wow, suddenly that looks simpler, and it even has a 2-dimensional structure, a grid. Let me rotate that a little bit. Let me now turn it into an actual grid. Do you know what this is called when we fill that grid? Starts with D. Yes? Dynamic programming, exactly. So this is how I like to explain dynamic programming. You have this absolutely intractable problem. Equivalence classes, group them 2-dimensional grids, dynamic programming. That's exactly how it works. And the trick, you also saw that in previous lectures, the trick is to fill the grids recursively, but now it's going to be what? The complexity? Polynomial, who agrees? Quadratic, right? Because it's just about filling the grids. Now we no longer have this exponential. Yeah. All right, so this is the trick. And now we just write down the distances here. So the idea is that the semantics, because there's plenty of conventions, the number that is in a specific grid like here basically gives you the distance between all the way to here. So that would be CA transformed to 8, right? And then the number is here, and then you fill all the numbers. So right, so this here would be from CA to 8. This here would be from cat to just A, right? And so dynamic programming, we just start filling the boxes like here. right? The difference between absolutely nothing and k letters is k, so that is easy to fill. The difference between k letters and nothing, we just remove, so that's easy to fill. And then we start going left to right and top to bottom, right? So here we try to find the minimum distance to go from here to here. So we have to look at, do we come from here, do we come from here, or do we come from here, right? So if we come from here, it means we get back to a known problem of transforming the empty string to the empty string, and then we just replace the C with an A, right? So that would be this here. So here the distance is 0, that would be +1, would give us one edit operation. To go from C to A, it's just replacing C with A, substituting A for C, if you remember the English lessons. Possibility number 2 is we recursively know how to solve the problem to transform C to the empty string. And after solving that problem, we just add the A, and now we have from C to A, right? So that is the recursive part, and then we add A, and now we know how to do C to A. So that would be 1 + 1 would give us 2 operations. And finally, the third way of doing that is that we know how to turn the empty string to A, and based on that, all we need to do to transform C to A is remove C, and then we're back to a known problem. We can just do whatever is done here. Okay, so this is the diagram. So we have the choice between the three. 1 + 1, or 0 + 1, or 1 + 1. And we take the minimum of that. What is the shortest? And the minimum of 2, 1, 2 is, everybody at the same time, the minimum of 2, 1, 2, you need to be woken up, right? 1, exactly. Yeah. All right, you know, I did it last Saturday. There was a math championship with primary school kids, 9-year-old, 10 years old. Everybody was screaming the answers in the classroom. They are much less shy with 9 years old. It's incredible. Anyway, so here we do the same recursively. We go left to right, top to bottom. But here there is a little bit of a difference between because the letter in here is the same as the letter in here. So A and A. So basically we do these three things. But here we don't add 1, we add 0, because replacing A with A doesn't cost anything, right? So that is the case in which the diagonal one, we don't add 1, we add 0. So we have the mean of 3, 1, 2, which is, yeah, exactly, like the primary school. Very good. We are young. All right, so 2, and so we complete. And finally, we arrive to the result with cat to 8, which is the result right here. And what's nice is that if you put back pointers in there, you can backtrack all the way to the intermediate operations that happened in between. So you see 2 here would basically correspond to removing the C and adding back the E, right? That was just a brush up, because since you already know that, who remembered that? Okay, how it works? Okay, so this is the Levenshtein distance. So that's exactly what we are going to do. If we want to spell check a word, we can just compute the Levenshtein distance between every single word in the vocabulary and the query. But as you can imagine, I told you the order of magnitude of the size of the vocabulary can be 500,000. That's a lot of things to do. So do you really think that Google is going to compute 500,000 Levenshtein distances in real time every time you type a query? Probably not, right? They probably optimized a little bit. So it doesn't quite work like this. We need to be a bit smarter than that. It's not as simple as that. And what we can do is pre-select some terms for which we can compute that distance. So not all of them, but pre-select them. And guess what? We are going to be using k-grams for that, the k-grams that we've seen before. The idea is that we are going to look at the k-grams of our query, and we are going to look at the k-grams of the words that we have in our vocabulary, and we are going to look at the Venn diagram of these k-grams, right? And then either they intersect a lot, like on the left, or they do not intersect a lot, like on the right. And then you can conclude if the words are similar or not, right? So on the left, that would be very similar. They have a lot of k-grams in common. And on the right, not very similar. They don't have a lot of k-grams in common. Here's an example with the mistake computer. You forgot the O. And so you want to see, could it be that the correction of computer is computer? So you have all the k-grams of computer in this part of the Venn diagram. Then you have all the k-grams of computer on the right part. These are the ones that are in both, that they have in common. These are the ones that are only in computer, but not in computer. And these are the ones that have a mistake that are not in computer. And so we are interested at looking how large is the intersection of the Venn diagram. So that's another example of words that have absolutely nothing to do with each other, computer and root. And you can see here the number of k-grams in the intersection is very small. So perhaps our first solution is to count the number of k-grams that we have in the intersection, and that tells us the similarity. For whom does that make sense? Right? Awesome. So let's try that. So let's have an incoming query, computer. We figure out all of the 3 grams. I'm taking k equals 3 here, so all the 3 grams, and we look them up right here. Here they are. And we find that in here we have computer, 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 Terran. Sorry? Oh, sorry, no worries. Okay. So computer, 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 Terran, and computer. All right. And so these are our candidates. All of the words that contain these k-grams are potential viable candidates for spelling corrections. And we can take these and do the comparison like this, with these diagrams like this. So if we do the comparison with computer, we will find that they have 5 3 grams in common. I've already shown you the Venn diagram for that one. And for Terran, they have 1 diagram in common, 1 3 gram in common. That is the TER, right? And by the way, how do you know? You don't even need to draw the Venn diagrams. Just look at here, the index. That already is telling you the k-grams they have in common, right? You can just read them from the index. So you can just count for computer 1, 2, 3, 4, 5, and for Terran, just 1. So maybe we could have some threshold and say, okay, if we have more than 3, then we just add it to the list and we are going to run the search on this word, computer. The problem is that it doesn't work. And I have an example here. If we take a threshold of 3 of the word board and boardroom that have nothing to do with each other, I don't see how anybody could make a spelling mistake and type boardroom instead of board. And I'm thinking maybe with autocomplete or something. But anyway, they have nothing to do with each other. And they still have 3 grams in common. So that's not okay. We cannot just put an absolute threshold of the count of the number of k-grams. So if we cannot take the absolute count of the number of k-grams, what could we do? Yes? Yes, absolutely. We can take a percentage, so relative count, compared to the overall size in here. And that's exactly the idea. We want instead to renormalize this count by dividing it by the total number of k-grams that we have in the union of the two. So the cardinality of the intersection divided by the cardinality of the union gives us a percentage. And the higher the percentage, the closer the words are going to be, right? So for example, board and boardroom, now we have a percentage of 25%, right? 3 divided by 12, and that is not so good, right? Computer and root, here we have a percentage of 9%, 1 divided by 11, right? And now computer and computer, we have 0.5, right? So you see now it's starting to be able to discriminate the terms that are very similar and those that are not very similar. As a comment aside, you notice that I did not call it the Jacquard distance. I called it the Jacquard coefficient. Who can tell me why it's not a distance? When you have a distance and 2 words would be very close, what is the distance like? Close to what? To 0, right? The distance gets close to 0 when it's the same. But here, When they are the same, it goes to 100%. So this is not a distance, this is the opposite of that, right? It grows as it becomes more similar. So this is why we don't call it a distance. Distances, it's something that is studied by mathematicians as metric spaces that has a research interest of its own. Then there's the triangular inequality and so on, all that sort of things. So basically, anyway, it doesn't qualify as a distance. We can build one that you could call the Jacquard distance by doing some cooking on top of the coefficients. But as is, this is not a distance. So just Jacquard coefficients, and we just want it to be as close to 1 or 100% as possible. Okay, so what we can do is we get the k-grams for the query terms. We look them up in the k-gram index that gives us a few candidates. We can compute the Jacquard coefficients based on these k-grams instead of the absolute count. And then we keep the terms with large Jacquard coefficients. Can we do it efficiently? It seems like no, because that seems like a lot of calculations to do, a lot of counting, you know. But in fact, if you figure it out, if you figure out every one of the components of that division, you actually realize you have everything to do it from the index. Because what is on top is the cardinality of the intersection. That's the count. That's the one we already had before, right? You just count the number of k-grams that you see in the index for which the corrected word appears, right? So that we can get. That's the numerator of the fraction. And then the denominator, that's the cardinality of the union. Who remembers this magical formula that you probably learned in first year, maybe even in high school? The cardinality of the union based on the cardinality of the two sets and the cardinality of the intersection. You remember that? Who does? Okay, you know, so cardinality of the two sets added minus the cardinality of the intersection, right? You remember that. All right, so we can actually figure that out because the query terms k-grams, that's basically a constant. You just do it once on the query and you have it. Then you have the number of k-grams for the found terms. That is exactly what you can count from the results you have in the index. And the intersection, we already have it because that's the same as up there, right? So basically, we are able to do that efficiently. And you can even pre-store the found terms k-grams. You can pre-store them in the index. If you don't even want to compute them in real time, you can just put them in there. Like computer has 8 k-grams and Terran has 6 k-grams. Who agrees that now, with just this, we have everything we need to very efficiently compute that division? Who agrees? Right? Very good. Okay. All right. So this is what we find in our example with 5. 5 is the intersection. 8 is we take it from below computer. That's the pre-computed found terms k-gram, which we have right here. And then we have 7 here. That is just what you do directly here just once with the query, right? So you have the 7 and minus 5. 5 is just repeated from above. So that is 50%. Now in practice, what people are going to do is a mix of the two. They are going to use the k-grams for a pre-selection of the words, and then they are going to be using the edit distance, the Levenstein distance, for the filtering for the words to keep. All right? Everybody with me? Okay. Very good. So that was it. That's the use of the k-grams and the edit distance and the Jacquard coefficients for spell checking. Now, there's other ways to do spell checking. One of the ways is to look at the context, the words around the word that we are looking at. For example, here, there's a mistake. Who agrees that if form here has a spelling mistake, who agrees that out of the context, you could not tell me it's a mistake? Right? Because the word exists, right? So it's based on the context that we know that there is probably a mistake because the 3 are okay. But then if we look at the other words that could be around, for example, looking at bywords, you see that there's graduate from ETH, so that kind of points you to the correction. And in fact, this is actually very old. But now you probably see the LLMs coming. Who heard of attention? All you need is attention, right? The famous paper. That's exactly the idea. The idea of attention is to link a word with the words that are around in some way, with matrices and linear algebra. So here we already start seeing the premises of what was going to be LLMs, this idea of looking at the words that are around. Okay? And finally, there is yet another way to do some spelling correction that works in English. You would have to design another algorithm for other languages. It's based on how the word sounds. The idea is that you take every word from the dictionary, from the vocabulary and the query, and you put them in some sort of mixer that spits out some 4-character fingerprints, right? So here's the idea. I'm going to be doing it on 6 examples to show you how this works. We have a conversion from letters to digits that looks like this. This is my conversion table. And I'm going to replace the letters by the digits. Now you can see why it makes sense, because the first one has kind of the vowels and what is kind of almost a vowel, like the y, like 2 eggs, 3 eggs, it's almost vowels. So A, E, I, O, U, and W, I, the H that is not always pronounced. All that goes to 0. Then we have B, F, P, V. These are the labial consonants, right? Those that if you speak them, you realize it comes from the lips. Then G, K, S. So they grouped the I think it's called the K, coming more from the back, and S. So the ones that whistle a little bit. Then DT, these are the dental ones, and then MN, these are the nasal consonants. So you see how it's basically based on the English pronunciation, right? So you basically associate with this kind of 1-digit fingerprint. And what we're going to do is we're taking these words and we are going to replace the letters by the associated digits, except for the first one. The initial letter of the word remains, but the other letters are replaced according to my lookup table. Who is with me? Right? This is how it works. So the 0, keep in mind the zeros are for the vowels, and the interesting information is in the consonants. Right? Next, we remove duplicates. What I mean here is when you have 2 digits that are the same and that follow each other. An example of that is the 3-3 that is right here. 3-3, that becomes just 3. And here it kind of makes sense because letter, TT is pronounced T, right? It's so this is why we group them together, and we forget that it's repeated. I think it might be the only example of that actually on that slide, but it can happen at many places. Then we remove the zeros. This is when we remove the vowels. In fact, there are even languages that work like that. Like in Arabic, you don't have the vowels. You just have the consonants when you write them, except maybe in children's book. So we remove the vowels in there, and we cut after just 4 characters, so the letter and the 3 digits. If we have less than 4, we just add zeros, like we did for L36. So we have L360 in here, right? And Z62 becomes Z620. So we pad with zeros or we cut after 4. And that here is the fingerprint of the word. That is kind of some compressed version of the way the word is pronounced. Very, very highly compressed, right? You would not be able to figure out the word from that. And so the idea is that when you enter a word in the information retrieval system, it fingerprints that word into some fingerprints and then compares them. Now, do you see that computer and computer, the one with a mistake, have the same fingerprints? That's because it's just a vowel, right? If we focus on the pronunciation of the consonants, it's the same. And now you can see how with this fingerprint, you can build yet another index that recovers the words from the fingerprints, another inverted index. And now you can locate the words that are pronounced in a similar way. Who would be able to build a system like that? You have everything you need, right? You have the algorithm for the fingerprint. You know how to build a standard inverted index, trees, and so on. And yeah, that works. All right. And so you see the link now with spelling, k-grams, the edit distance, the Jacquard coefficients. That's called the Soundex algorithm, this fingerprinting based on the pronunciation. And of course, you would have to do it again for other languages. It's probably easier to do in a language like German or Italian, where there's really a very close relationship between the way that we write words and the way we pronounce words. French would probably be difficult because here it's total mess, the mapping between pronunciation and the words. That brings us to the end of this lecture. So this is chapter 3 of the book. Who read chapters 1 and 2? Ah, awesome. I like that. Okay, very good. If you haven't read them, please read them. It's very important. This is the material of the course. It also gives you a different perspective. Who has already read chapter 3? Who will read chapter 3? Okay, very good. So I think you followed well, so I think you deserved an early break. We have 4 minutes left, so I can let you go now for a break, and then we'll continue with index construction. And here, what will be interesting is we are going to build indices for larger and larger and larger collections, and even for collections that wouldn't fit on the computer. I will show you how we can do that. So see you in 4 minutes. Thank you.